wants to take a shot?
The chances you have out of a hole.
Out of a hole. What do you mean by hole?
A total, I don't know, total amount, like the card deck, there's 54, so you have.
Okay, so a card, you have so many decks. Okay,
Yeah.
so out of given number of tries.
Yeah.
Ooh, draw. Change. Let's just see. Chances you have out of a whole. Chances you have of a group of things.
That's what I have. Is how many times an action will occur.
Events, maybe actions. What did you say?
How many times an action will occur?
Action. And you all put examples to go with your definitions, right?
Yeah.
Action. Give me an example.
Like rolling 2 dice, and what are your chances of snake eyes happening in 10 rolls?
Okay, so rolling 2 dice. So then we're adding up what we get on the dice. So snake eyes would be 1, 1, or 2. Okay. And then Hillary was thinking like 52 cards in the deck, and getting a particular card maybe. Okay. And then Kelly?
Any type of game playing the lottery?
Any kind of lottery games? Ooh, yeah. What is probability? So that's an example. What would the definition to go with that example be?
First one.
The first one, chances you have on a whole group of events. Okay, so there's
You have one chance.
6 numbers, 6 spots to put a number, and you have a whole lot of numbers to put in there.
But isn't that
And we'll look
odds?
at the lottery
It is
later.
the odds.
Yeah. No, well,
Probability.
odds. Okay, so odds keep coming up. So let's just get it out of the way right now, and we'll come back to probability. Odds has a specific definition. It's there's 2 kinds of odds. I'm going to do odds in favor, and then there's odds against. And if you gamble, actually usually see odds against posted. I'm going to do odds in favor. So odds in favor are the favorable outcomes. I'll now define this more carefully later. Divided by unfavorable. Outcomes. So often when we're flipping a coin, people say 50-50. What does that mean? That there's 50 favorable outcomes over 50 unfavorable outcomes? Well, really, there's 1 favorable outcome over 1 unfavorable outcome. Like I want heads, not tails. And 1 over 1 is the same as 50 over 50. Sometimes odds are defined as the probability of what we want to have happen divided by the probability of what we don't want to have happen, in which case this is 50% over 50%. Same idea. Christian?
Originally, what I had written down was opportunity times odds plus natural abilities and disabilities.
Holy crap. Let me process that again. Okay, so opportunity times odds plus natural abilities and disabilities. Interesting. What do you mean by opportunity? Like number of times?
Opportunity could be like chance, so like the opportunity of getting a 6 on that 6-sided die is 1, and the odds would be how many times do you get to roll the dice.
Okay, so you're using odds in a different way than I am. So we got to be a little bit careful about that because we want to use the right language. And this is the definition of odds in favor. Guess what the definition of odds against would look like?
Unfavorable.
Yeah, it would just be unfavorable outcomes over favorable outcomes. And we need to get more specific about what the heck an outcome is. Okay. And so I'll define that more carefully just today. All right, so Greg, you said something earlier about probability. What did you say?
I said the chances of a particular action or event happening in a given number of tries.
Chance of action or events happening. And then you have in a given number of tries. Okay.
That was without answering.
In a given number of tries. Okay, so we're all pretty close, right? So we're just gonna get a better definition. But we all have this intuitive understanding about probability because we've been seeing it all of our lives. And so we need to be more careful. So the bottom line is there's different situations where probability comes up. So let me go over a couple of situations and see if we can do probability based on that. Oops. New page. New page. There we go. All right, so for example, so I'm going to go backwards. I'm going to give my examples first, and then I'm going to try and find probability. Flip a fair coin. What the heck do I mean by fair? Anybody?
Not rigged.
Not rigged. Christian?
Not double-sided.
Not double-sided. Okay, so what else could I mean by it? What's that?
Different sides.
Has different sides. Coins can be weighted, so you could have a heavier material on one side than the other. You could also have it so the design on one side makes it lean toward that side more than the other side. Kelly, kind of like buttered toast seems to fall butter down.
Would you ever know that?
Both sides are equally the same.
I have as much chance to end up with one side as the other. Okay, so that's what fair means. One isn't more likely to occur. So we got all these words popping up. Like we're using probability, chance, and likely a lot. What the heck do those mean? So we'll get there. So flip a fair coin. Fair is kind of a questionable term, but we're getting an idea for it. And so the chance or probability, those are used interchangeably, of getting a tail is what?
1 out of 2.
1 out of 2. Somebody might say 50% or 0.5. Okay. Another example. There we go. Gary shoots free throws. He got 4 out of 10 in. What's the chance he'll get the next one? Yes.
1, 11.
11th.
1 out of 1.
One has a 100% chance he's going to get the next one.
No.
Wait, so you get 10 shots?
No, what? So,
You made 4?
so you watch Gary shoot 10 times.
So if
He got 4 of them in. He's about to
to.
shoot again. What do you think the chance, based on that information, is going to get it in?
1
5
11.
chance.
2 out of 5 chance, 4 out of 10 chance, 40%.
40%.
Yeah, based on the observation so far, we think he's got a 4 in 10 chance because that's what we've observed. Right? Probability is based on some observation. Bottom line. 4 went in. That's favorable. There were 10 total, and we were getting at that idea with the other ideas. Christian reduced it to 2 out of 5. I called it 40%. All different ways of saying the same idea. That is slightly different than the flipping a coin thing. Would you agree?
Why would it be 4 out of 10 when you're shooting 1 more?
Because he made 4 out of 10 shots, so.
Yeah. So
So it's a 40%
so here's the thing.
chance.
So here's a new idea we got to get to. I flip a coin 10 times. How many tails do you think I'm going to get?
7.
4 out of 10.
Who knows?
5.
5, right? Since half of the time I expect to get a tail, I would expect about 5 to be heads. Now it could be 7, it could be 4. Who knows what's going to happen? But I expect to get about 5, right? So I just got 5 out of 10, and I'm going to flip the coin again. Is the coin aware that there were just 5 heads and 5 tails?
No.
It is totally
Oh,
unaware.
so then it's 50% chance that you're
Right? So there's still a 50% chance that's going to happen.
Okay.
Now, me throwing baskets is slightly different, one of two things could happen. I could be nervous I'm gonna miss after getting 4 out of 10, because that's pretty damn good for me. Or I could feel like I'm on a streak, I'm gonna nail it. Woo, look at that. 100% chance I get that in. Notice I use God. So the idea I'm getting at is what's called independent. Are the events of shooting a free throw or flipping a coin independent of each other? So knowing I just got ahead, does that have any effect on the next flip?
No.
And then you have to figure out, knowing Gary's going to throw again, that he just got it in, does that have any effect on him getting it in again? And you can argue it either way. You could say it's independent. On the other hand, there is some statistical evidence that people do go on streaks, and maybe me getting it in, depending on my nature, could mean I'm more likely to get it again.
Yeah, because you find your sweet spot.
Or it could be something else clicks in my head, and all of a sudden I'm nervous. Oh shit, I threw it the wrong way.
That's me.
So the independence of me shooting in the basket, that's questionable. Sometimes we just make believe it's true to simplify the problem. So that's the idea of independent events. Okay, I'm going to do another example. Oh, wait, I got to do something else first. Like Hillary's always inspiring me to do something distracting, like check my email or text or see what the weather's going to be like.
See what kind of food you should eat.
Weather.com. What's your damn phone down, please? That's you.
I'm not even looking at it.
It's in your hand and you were just touching it. Okay, where do we live again? We live, oh, this says allow your location. That's Washington, D.C. I'm not in Washington, D.C. I'm in 97801.
I read something today about how, you know, that big crack in the earth, whatever, is supposed to be happening. How the tsunami is going to come. Have you ever read that?
Tectonic plate.
Yeah.
Tectonic plates are going to shift?
Yeah,
Okay,
I read that today, and today they put a specific date on
okay.
And what was that
Well,
specific date?
it, June
Yeah.
7th through 10th.
Okay.
Just one of those 3 days.
All right, so let's see.
2016?
Yeah.
Are they giving me, oh, check this out.
4 days, whatever.
Don't go west of the I-5.
Yeah, but
Okay,
they
so
said that it can hit
in-
all the way
okay,
all
shh,
to
shh,
Quebec.
In Pendleton, there's a 0% chance of precipitation. Let's go look somewhere else.
Athena.
Let's go a little farther.
Let's go
to
Eugene.
Seattle. Oh, Eugene, okay.
It's always-
Yeah, they're both rainy places.
Oregon. Oh, I didn't spell that right.
It's
Oh, geez, what the hell? How did A get in there? Huh. Oh, stop it.
Orlando.
Spell it again.
You get it right that time?
Yeah. There you go.
Okay, come on. Come on, Weather Channel. Hello. Earth the Weather Channel. No results found.
Type it in again. It popped up there.
Eugene, Oregon. There we go. Okay. Come on. Oh, no chance in Eugene. Okay, let's go check out Seattle.
0 chance.
You just looked in Seattle?
Yeah, I got a friend lives there.
Hey, you're supposed to put your phone away.
Or turn it on silent. Though there is a flood warning. It says up there, Eugene, flood warning. Oh, that's Seattle.
Why does it say?
Flood warning, but no.
0%.
0% chance right. Okay, let's check. I grew up in Rhode Island. Let's check Smithfield. There you go. Any chance of rain there today? This is driving. Come on, give me a good example. I'm just gonna have to
60
shoot up.
tomorrow.
Okay, so tomorrow,
And
No,
90
on
90
Rhode
on
Island.
Tuesday night.
where my mother lives, it says there's a 60% chance of rain tomorrow. What the hell does that mean? That's a probability, isn't it?
Yeah.
Okay, so that's another example. My claim is it's different from the flipping the coin. It's different from the throwing the thing in the barrel. So, stop it. What it is. There is a 60% chance of precipitation in,
Who's this?
I would just call it Rhode Island. It's a pretty damn small state. Tomorrow. Do you know Rhode Island is about the size of Umatilla County? There's 1 million people there. Okay. So my claim is that's different than a different kind of probability than the other two. What does it mean to have a 60% chance of precipitation in Rhode Island? Christian?
Does that have something to do with saying because 6 out of 10 times when the weather does this, it rains? It's saying that's why there's a 60% chance.
6
Because
out
the
of 10
weatherman
times when
said
the
so.
weather does this, it rains. That's an excellent interpretation. Kelly?
It depends, years before, would it be?
Yeah? Oh, years, similar days before it rained 60% of the time. Yeah, that's pretty close to what it means. It doesn't mean it's going to rain in 60% of Rhode Island. It doesn't mean it's going to rain 60% of the day. Right? Those are things it definitely doesn't mean. But under similar conditions, 60% of the time it rained. So let's suppose we had 100 similar days. It rained on 60 of those days. The harder question is, how did they come up with that? And that's a combination of data people collected and these crazy computer programs that try and mess around and stuff. And they come up with these predictions. And it's a very hard thing to do. But that's one way to interpret that 60%. So let's get back to the other ways. And we have to be a little more specific about what things mean. What the heck do we mean by outcome? How is chance different than probability? There's something to address next. Let me put this in difference. So, there we go. So one definition of probability favorable. I'm going to use the word outcomes again. I'll find that in minutes. Over total outcomes. And this is usually referred to as a theoretical probability. And for something to be a theoretical probability, you have to know all aspects of the situation. And knowing everything is a pretty rare field. Know all aspects. Often we replace know with believe. Maybe I'll do that here, just for fun. So that coin I had a minute ago, go put it down somewhere else. Ah, there it is. Okay, it's a pretty ordinary coin, right? So, quarter, got my eagle, got my head. Eagle. So, and remember the idea of considering it fair? So fair means I have no reason to believe that it will show heads more than it'll show tails and vice versa. Or that the person flipping it has no control over how many times it flips and how it lands. Right, so that's total belief. There's one favorable outcome. I want to see tails. There's two possible outcomes, heads or tails. Do you ever get a quarter balance on its edge? So is it possible that you could flip it and it could land on its edge?
I've seen
In a cartoon.
In a cartoon, I can't even get it to balance on its edge.
I've
so
seen it happen before.
it seems ridiculous. A nickel's more likely, it's wider, it's got a flatter edge maybe, but we can say that's pretty remote, we can ignore it, and we have to do that sometimes. But this is just one definition of probability. What's an outcome? So sometimes instead of outcome, we'll use the idea of a simple event. So by here, by outcome, I mean simple events. What makes an event simple, do you think? Like, example, head is, let's see, versus tail. If it can't land on its edge, those are the only two options, right? That's about as simple as it gets. Think about rolling a six-sided die. How many ones are on my six-sided die? Just one of them. That's pretty simple. What about getting an even number? Is that simple to you? Well, how'd you get 1/2? There's 6 possibilities.
But there's only 3 even numbers.
There's 3 even numbers. So if you can break an event down into other events, it ain't simple. So a simple event means you can't break it down into smaller events. And another thing for the definition I just gave, we want each simple event to be equally likely. If that's not the case, the definition of probability I gave doesn't work. So I'll give you an example. So I have a draw. This is hard. A drawer of socks, and mostly I like black socks, but I have a couple white socks. I have these really cute green socks. So in my drawer of socks, they're mostly black, but I have some whites. I can draw whites. Orange, green. So as I color the black ones in, and these could be white socks. There's a black one in there, and then I do have that magic pair of green socks. And so that's each circle here represents a pair of socks, right? So I'm going to pull a pair of socks out. I'm not going to look. So often we use, when we're talking about probability in math classes, we use the letter P parentheses to talk about the probability of something. And I could have the probability of black socks. I could have the probability of white socks. And I also have the probability of getting green socks if I just reach in and grab a pair. So in some sense, you could say, well, I have 3 simple events here. I have black socks, I have white socks, and I have green socks. Do you believe I'm as likely to pick out a pair of green socks as I am black socks?
No.
No, that's not true. So it's not equally likely that I'll get black and green, because there's different numbers of each. So in some sense, black is a simple event. On the other hand, it's there's more than one way it can happen. So that makes it a little more complicated. So this is a little bit different because we don't have that each one is equally likely. But I can clearly see there's 4 pairs. So how many sock pairs do I have altogether? There's 7, right? So what's the chance of getting black?
4 and 7.
4 and 7. And how about whites?
2 out of 7.
2 out of 7. And how about green?
1/7.
1 out of 7. one thing that should be true, even if your simple events aren't equally likely, when you add up all the simple probabilities, guess what it should add up to?
7.
It should add up to a whole, 7 sevens, 100%. Yeah, so this adds up to 7 sevenths, which is 1, which is another way of saying 100%. So anytime you add up the simple probabilities, you better get 100%. Doesn't matter whether you're talking about it as decimals or percents or fractions. We can talk about it either way. Sometimes it's easier to talk in fractions. 4 sevenths, 1/2. Sometimes the fraction is easy as a decimal. That's 1/2 as a decimal, 0.5, right? So when we were flipping a coin, the probability of getting a tail was 1 out of 2, which is 0.5, or we could say it was 50%. Those are the common ways of talking about it. My socks were a little trickier. The probability of getting green socks, that was 1 out of 7. Unfortunately, 7s doesn't make a good decimal, does it? Why not? What kind of denominators make good decimals?
Even.
Even make good ones. Okay, what else? Kelly?
5.
Kelly? Oh. What were you saying? 5s and 10s. You forgot? Okay. Yeah, Greg said if the denominator is made up of 5s and 10s as factors, it turns out nice. If there's anything else in the denominator and it won't go away, then we have trouble. And so 1/7 is 0.142857, and then it just repeats that pattern over and over again, which makes it rather a pain in the butt. So in this case, if I want to do anything but a fraction, I have to say it's approximately, like as a percent, I could call that what, 14.3%? Is it exactly 14.3? No, but it's close. Do I hear Debbie out there? Hi, Debbie.
Yes. Hello.
We're having fun with probability. How long you been there?
Just like 5 minutes.
Okay, so, all right. So all the stuff I was just doing, those are what I call theoretical probabilities. Let's look at the other kind. So the other kind when I was doing the free throw. Okay. The free throw kind are called experimental probabilities. And we have to be really cautious whenever we walk into a situation with probability, and we have to ask ourselves, do we know everything there is to know about this situation? Or are there things we don't know? If we don't know stuff, we're probably in the experimental realm, not the theoretical. Theoretical means we believe we know everything there is to know. I see my coin. I see it as 2 sides. I see my dice. I see it as 6 different numbers on it. So the example I was going over earlier was me shooting free throws. And so in this case, to define probability, it's going to be equal to favorable, not outcomes, but observations over total observations. Similar idea. But slightly different. So the probability Gary gets shot. The only way we can really measure that is by watching him shoot so many times. And so let's say we watched him shoot 100 times. And of those 100 times, he got it in 37 times, say. So then, based on those 100 trials of the experiment, and sometimes we call it, instead of observations, we'll say trials. He got 37. So then we can say his probability is about 37%. So is that likely to change over time? Yeah, someday we'll have watched him do 1,000 shots. Maybe he'll get 370 in, maybe not. Maybe he does better, maybe he does worse. All right, let's try, so we have theoretical probability, we have experimental probability. What about the weather? Oops. Oh, odds, right. Here. 60% chance of rain. Did someone really observe 100 days of similar conditions in a particular place and it's exactly 65 rain? No, it's a combination of things. And so then there's the expert's opinion. And that's going to be made up of a bunch of different things. There'll be some theoretical stuff in there. There'll be some experiments in there. Sometimes with experiments, we run simulations. Simulation is kind of a make-believe experiment. Slightly different. And then there's just opinion. Otherwise known as belief. So we can break probability up into 3 kinds. The kinds we know everything about, the kinds we have to watch and see, and then we put a whole bunch of stuff together and make a wild ass guess. I think that's what this is also called. These are called EWAG, educated wild ass guess. Don't say that in the kids' classroom.
Unless one of them says it first.
Okay. So let's see, what other ideas can we do there? I think we should play now. Oops, just double check something. Do that later. All right, so let me do one more example and then we'll play with one of the activities. Brittany brought up the idea of rolling 2 dice, which is like craps. Oops. Tools disappeared. There they are. So we're going to roll 2 6-sided dice. And we're going to add the results. And so what we want to do is kind of figure out what's going to happen. So I'll show you a couple of ways to organize that information. When you have 2 things happening at once, a table is a nice way to organize it. So I could say there's dice number 1 going one way on the table, and that dice could be a 1, 2, 3, 4, 5, or 6. And then there's dice number 2 going the other way on the table, and that could be a 1, 2, 3, 4, 5, or 6. And so what I end up with if I do that is a grid that has 6 rows and 6 columns. So if you could, for me, fill out what the possible sums are. So dice 1 gets a 1, dice 2 gets a 1, then in this first cell here, I get a 2. So fill out the rest of it and then we'll talk about it. doing something like that. Really cool patterns here.
Ooh, I found one.
What?
Going diagonally,
Uh-huh.
2, 4, 6, 8 goes up by 2.
Oh, 2, 4, 6, 8, 10, 12 down one of the main diagonals, yeah. And the other
And then
diagonal?
are the odds, or yeah, so 3, 5, 7, 9.
Oh, right next to it is 3, 5, 7, 9.
And then
That's
it goes
kinda
back
cool.
to the positives, or the,
It goes even odd
Yeah.
diagonally.
And
From
then the other
upper
way, all-
left to lower right. The other way, from upper right to lower left,
it's the same
all the
number.
it's the same number, which is kind of cool. So I could say, well, look at this diagonal right here, 7, 7, 7, 7, 7. And 6, 6, 6, 6, 6, and 8, 8, 8, 8, 8. So there's some cool patterns that evolve in there. What's the most likely sum you think we'll get? What number will turn up more often when we roll 2 dice in that month?
7.
It looks like 7 occurs the most. There's 1, 2, 3, 4, 5, 6 of them. What's going to happen least often? 2 or
12.
yeah, 2 or 12 will happen least often. Yeah, because the only way a 2 can happen is a 1 and a 1. Only one way that can happen. Only way you can get a 12 is a 6 and 6. But there's lots of ways to get a 7, depending on which dice got which number, which is kind of interesting. So how many simple events are there in this situation?
And each one of those lines constitutes as a single event.
So that's a good question. What is a simple event here? So I'm summing the dice, so I can get a 7. But isn't there more than one way that 7 can happen? Yeah, so the simple events would be each way that 7 could happen.
36.
So the 7 could be the first dice gets a 6, and the second dice gets a 1, or the second dice gets a 6 and the first dice gets a 1. Those are 2 different ways that 7 can happen. Turns out there's 6 different ways that 7 can occur. So there's 36 simple events here. How many different sums are there?
36.
Well, no. As far as sums, those are the diagonals going from
Down to
from
6.
from bottom left to upper right. So there's 2 through 12, which is what, 11 possible sums. So there's 11 different sums we can have, but each of those sums can happen different ways, except for 2 and 12. 36 simple events, 11 sums.
Minus 2 and 12.
Well, yeah, but 11 wouldn't be able to do something different either.
Well, 11 can come up in 2 different ways. You could have either gotten a 6 and then a 5, or a 5 and then a 6. Okay, so I'm going to give you another situation to explore that idea. So let's go a little bit simpler. We'll come back to this. Suppose I flip 2 coins. Yep. It's not working. Please. Flip 2 coins. That's interesting. Things are losing the eraser. Okay, so let's see. I flipped 2 coins. Let's see. I like heads. No, I like tails, actually. There's usually something more interesting in quarters these days in the tail. Wouldn't you agree? So I like tails, actually. And so as far as tails go, one of 3 things is going to happen. I'm either going to get 0 tails, or I'm going to get 1 tail, or I'm going to get 2 tails. Agreed? Both could come up heads, no tails. I could get a head and a tail, or I could get 2 tails. Question: what is the probability of getting 1 tail when I flip 2 coins?
1 of 3.
1 out of 3?
One.
1/2?
1/4? Okay, so we got a bunch of different ideas. So one way we could solve, there's a lot of ways we can solve it. One way we could solve it is we could flip 2 coins a whole bunch of times. Should we do that? Let's have the computer do it for us. So the spreadsheet will do a wonderful job with this. I'm going to go to Google Drive and bring up the spreadsheet. So calculators, anybody have a TI on them today? Yeah. How many of you have TIs? Oh, awesome. We're going to do a TI experiment too. Texas Instruments, sorry. Clear, Texas Instruments. So let me bring up a new, we have 3 of them? Ooh, okay, yours is different, so this might not work. I have 2 of the same kind, this is going to be interesting. Google Sheets. So,
You're slow today.
okay, so let's say I have a quarter and a dot. And let's say I like heads, so a tail. A tail is a 1 and a head would be a 0, say. So most computers have random number generators, a couple of different kinds. So I'm going to use what's called RAND. RAND on a computer and a calculator, here it says it gives me a number between 0 and 1. Inclusive means I could get a 0, exclusive means I can't get a 1. But it can have any decimal in between up to a certain amount of places. There's another one called RAND between, which I like better. Okay. And what RAND between does is it picks an integer. Anyone remember what an integer is? Number is square root of 2 an integer? No. Is 1/2 an integer? Whole number. Whole number? Or?
Opposites.
They're opposites, like -1, -2, 1, 2, or 0, right? So if I choose RAND between, and I say, give me a random number between 0 and 1, that means it'll either give me 0 or 1. Those are the only options here. So I run it, and then I can fill it down. And so I just flipped that quarter. Let's flip it 100 times. Oh, shit. Oh, gosh. So this is going to be 100 flips. And it's supposed to be just as likely to get a 0 as a 1. Okay. Oops, one more time. It reshuffles them each time, which is kind of a pain. Cool thing, I can just fill that formula over, and it'll tell me. Do it. Okay. It'll also flip the nickel, dime. Okay. And so then what I could do is add these guys up. Sum, and beware, it's going to be jumping around. Most spreadsheets that you do a random number generator in, every time you hit enter or do something new, it recalculates the random number. So you'll see my 0s and 1s jumping around for a while. So I'm going to flip a coin, and this, for me, will observe whether I got 2. So, yeah, so this is the number of tails right here. 2 tails, and it's going to change each time. It's kind of freaky. And so then I can have the computer count up these for me. So I'm going to have it count up 2, 1, 0. So I can remember how to do that. Count equals counts. Range and the criteria. So I think what I'll do is I'll highlight all of these. A, and more commas, C2 through C1. And I want to know exactly matches A2. Okay, I counted 24 2s, and then I can just reproduce that one. Ones there are 0 means I got no. And so if I add those 3 numbers up, that should add up to 100, does it? 20, 60, 70, 80, 89, 95. Does that make sense what I'm doing here? So the computer found that 25 out of 100 times there were 2 tails, 46 out of 100 times there was 1 tail, and 29 out of 100 times there were no tails. So does it seem reasonable that I'm as likely to get 2 tails as 1 tail as no tails? Or does this data say that doesn't seem right?
Because the odds of you getting both the same coin is probably greater.
Let's run this again, right? So I'm just going to type something like a G, and it's going to reshuffle it. 30, 47, 23. So the dime being lighter, do you think that affects whether it comes up heads or tails more?
Well, not in this.
Now, not here, because here I'm just as likely to get a 1 as a 0, which is a head or a tail. Let's run it again, delete. So,
But even the same coming up is going to be harder to get than having one-on-one.
So here's what I think I would see. If I was just as likely to get 2 heads as 1 head as no heads, I would expect each of them to be about 33. That make sense? Is one of these areas coming out way more than the other? Doesn't it seem I'm twice as likely to get 1 tail as no tails? Now, so the way I stated the problem before, I did it on purpose to mislead you. So, and I misled some of you and not others, which is fine, because how many times is something presented in the news that's slightly unclear? Which means that there's going to be all kinds of different interpretations of it. So here's another way of looking at this. I'm going to draw a tree diagram. You remember drawing those before in classes? Yeah. So the way I'm going to do it, and I'll do a table too, just for comparison. The way I'm going to do the tree diagram is, let's suppose I always flip the quarter first. What's going to happen? What are the possibilities when I flip a quarter? It's either going to be a head or a tail, right? So basically this branches us into multiple universes. In one universe, we flip the head. In the other universe, we flip the tail. For those of you who like science fiction. And then we take our dime and we flip it. So let's suppose we're in the universe that got the head. Then we flip the dime, and that dime is either a head or it's a tail. We could be in the other alternate universe where we get a tail on the quarter, but what's going to happen when I flip the dime? Well, it's either going to be a head or a tail. There's no stopping that. Agreed? So how many branches at the end does my tree have? How many end results are there? There's 4, right? 1, 2, 3, 4. Yeah, there's 4 ends to my tree. And so what are the possibilities? Well, either if I follow the tree through this path here, that path says I got a head, then a head. Head for the quarter, head for the dime. The next path says I got a head for the quarter, but a tail for the dime. The next path says I got a tail for the quarter and a head for the dime. And the last path says I got a tail for the quarter and a tail for the dime. And if I'm counting tails, which is what I'm trying to do here, this counts 0 tails, this counts as 1 tail, that counts as 1 tail, that counts as 2 tails. So how many different outcomes are there in the end here? There's 4 different outcomes, okay? Are each of these 4 outcomes equally likely, do you think? Am I as likely to get a head as a tail for the quarter? Yes. Am I as likely to get a head as a tail for the dime? Yeah, in either universe I am. So at each stage I branch off equally likely. So what I think I end up with here is 4 equally likely events in the end. But there are 2 ways a single tail can come up. Either the dime could come up with that tail, or the quarter could come up with that tail. So although I stated the problem over here as just counting tails, the bottom line is there are 2 out of 4 ways that can happen for its probability. There's only 1 way to get no tails out of 4 possible ways. And there's only 1 way to get 2 tails out of 4 possible ways. So in order to analyze a probability, we have to look at all the details. That I was counting tails as an end result but I still have to look at the simple events that get me there. And so we always have to ask ourselves, is getting one tail a simple event? No, because I'm flipping 2 points. Which one got the tail? That's 2 different events. Does that make sense? Okay. I could have, so tree diagrams are very helpful in trying to analyze problems. Because I could throw a 3rd coin in you and see what happens. So let's see if we can extend this one more time. So what happens if we do a quarter, dime, and a nickel, and we want to count tails? So we've got a quarter, a dime, and a nickel. Is it LE or EL? There we go. LE. Looks good today. Quarter, dime, and a nickel. And again, I want to count tails in the end. What I want you to do is make a tree that shows what could happen. So we started that tree. You need to continue by branching one more time. Here we show quarter, dime, do one more set of branchings to throw the nickel. So extend this tree, one more set of branches. And then you want to count tails and see if we can come up with a probability. How many possible outcomes are there?
8.
There's 8. And I don't know if you remember, way back in Math 2:11, we talked about when you have different options, you can multiply the options at each stage to figure out what the total amount is. So how many options are there for the quarter?
2,
2. How many options are there for the nickel?
4, or 8.
2.
Oh,
Head or tail.
because-
Oh, yeah,
How many
that's right,
options
yeah.
for the dime? 2. So if we take 2 times 2 times 2, what do we get?
8.
8. And so that 8 tells me how many possible different things can happen. But I don't know what those different things are until I do something like make a tree. The hardest thing about probability is counting up what can happen. And we need some kind of system for that. So let's see, one option is head, 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 right? How many tails are in there?
None.
None. So this one leads to 0 tails. Let's see, we could then do a what? Head, head, tail. 1 tail. We could do a head, tail, head, going in order. That's 1 tail. Head, tail, tail.
2.
2 tails. Let's see, I've exhausted those 4 possibilities. So now I jump getting a tail on my quarter. So tail, head, head
1,
is a 1. Tail, head, tail
2,
is a 2. Tail, tail, head
2.
is a 2. And then tail, tail, tail is a 3. So now I can figure out what's the probability of getting no tails, what's the probability of getting 1 tail, 2 tails, or 3 tails. And those are the different possibilities. So let's see, there's only one way to get no tails, right? There's 3 ways to get 1 tail. And there are, what, 3 ways? Oops, let me switch colors there. To get 2 tails. Oops, Control Z, there we go. 2, 2, and 2. So there's 3 ways that can happen. How many ways can we get 3 tails? 1 way. So anytime we're trying to solve a probability problem, we got to explore it somehow. Often a tree can help. So I'm just going to summarize that in another table. Hang on one second, Christian. I saw your hand there. So I have some events versus the probability of that event. And my events here are no tails, 1 tail, 2 tails, or 3 tails. the probability of no tails happening was 1 out of 8. Probability of 1 tail was 3 out of 8. Probability of 2 tails was also 3 out of 8. And probability of 3 tails was 1 out of 8. And what do all those probabilities add up to if I were to sum them? Yeah, so the sum always has to add up to 1 if I have all of the simple events. And those would be the simple events here. Okay, Christian, what were you going to say?
I was just curious in kind of realization of the question. So when we looked at you throwing dice in the bucket earlier,
Yes.
many of the responses were chance of getting all 3 to win or one of them in was like a 1 in 3 chance.
Yeah.
But instead the diagram for Volcano would be more like this.
No,
where if you got
this is, so flipping a coin is a theoretical situation, so I know everything about it. Me shooting in the hoop is not something I can know everything about. And so the only way I can measure that one is observation. So making a tree there isn't necessarily helpful. So think about if you're into sports. Well, I guess free throws in basketball are a good example. Horse races. Was that horse races? Horse races is sketchy. So think about, I'm just going to go back to free throws for a second. So we can watch somebody shoot a free throw, and we can count how many times they go to the penalty and how many times they throw off the other. Other things people might look at is looking at the second shot. How often did the person get the second shot in when they got the first one? Those are conditional probabilities, and those analyze whether the events are independent or not. Does that make sense? So if the second shot, if say I have, it looks like on average I have 40% chance of getting it in. 40% of the time I get it in. If my second shot is independent of my first one, then my second shot should also always be a 40%, regardless of whether I get the first one in or not. But that's not always true. Right? If you look at, I know, for example, I've looked at it in soccer. The chance that someone gets a second goal in a game is usually higher, knowing, let's see, I'm not saying that right. If they're in or place to kick and they've already gotten a goal in, they're more likely to score than if it's their first try. Yeah. Knowing they got a first shot ups the probability for a lot of players of getting it in the game. Which is interesting. Okay, Kelly, what were you gonna say?
Baseball?
Baseball, like batting average? Yeah, and interesting thing about batting averages, don't they change every year?
Yeah.
A little bit. You know, finally they start to stabilize at the end of someone's career because they've been at bat so many times. When the denominator is really big, a few times at bat is not going to change. Right? But it takes a lot of data to zero in on something like that. Yeah, so we can't quite do the same thing. Okay, so I think I did way more of this than I wanted to. Oh shit, really? Is that the time? You guys are all still awake. Let's take a look at the spinner lab. I got way carried away. All right, so spinner. Here we go. So the way the spinner lab is going to work is we're going to pin. You can either play against yourself or play against somebody else. So we could spend the last 10 minutes messing around with this. I have some cute little plastic clear spinners that you can put on top of that page. Alternatively, if I were at home, I would look for something like a paper clip. And the paper clip can be bent in such a way, mess this one up pretty bad. There we go. Like the picture on the screen here. So all I do is I put my pencil down in the middle here, and I put the loop of the paper clip on it, and I just flip the paper clip. So you can make your own spinner. So the question is here, let's see, spinner A has 1, 2, 3 different numbers it can get, a 2, a 4, or a 9. What's the probability the person using spinner A is going to get a 4?
3.
Yeah, 1 out of 3. Because that arc is the same size for 4 as it is for 9 as it is for 2. How about spinner B here? What's the probability someone's going to get a 7? It's also 1 out of 3. So if we play spinner A against spinner B, like maybe Hillary on spinner A versus Brittany on spinner B, who do you think is more likely to win when they play against each other? So what happens is they both spin at the same time. Person with the biggest number wins. Is it just as likely that Hillary on spinner A is going to win as spinner B? What do you think?
Yes, because they got it.
So you think they're just as likely because they add up to the same? Oh, do they really? 9, 10, 11. That adds up to what, 15. And the other, both groups of numbers add up to 15. That's interesting.
B has a significant advantage because even though 9 is the biggest number, and if they got 9 no matter what they get on B.
Okay, so spinner A gets a 9, they win every time they get a 9. Okay, but
if on B, if you roll a 3, yeah, you can only be 2. But 5 beats both 2 and 4, and so it's 7.
5 and 7 beat 2 and 4
So
on
you
the
have-
other one. So you think B might have a slight advantage even though A is the biggest number? Okay. So here's another thing to think about. We might say, hey, these are equally likely because they have an average value of 5. 15 divided by 3 is 5. But if there's 3 possibilities for A and 3 possibilities for B, how many different possible outcomes are there in this game? 3 possibilities for A, 3 possibilities for B. There's what? Not 6. 9. Remember a coin is 2 by 2, 2 coins? So there's 4 outcomes? Yeah, so there's 3 times 3, or 9 different ways this game can turn out. Okay, so if there's 9 different things that can happen and there's two people playing, is that going to be fair? Split 9 things among 2 people, what's going to happen? One person gets more, one person has less. Yes, somebody is going to have an advantage here. And so we're going to try to figure out who. So the first way we're going to try and do it is you're going to play the game 30 times. And you're going to mark down. So we're going to do a couple different things here. You're going to mark down how many times you get a 2, how many times you get a 4. Now, their sheet here for doing this I don't think is a good idea. Here's the way I think you should write it down. There it is. Okay, so here's the way I think you should write it down. I would make a table like this. 3 columns. We'll do an advanced one with a 4th column later, but we have what we'll call the trial, what A did and what B did. So you guys just play with me right now. So here, Hillary and Brittany are going to play against each other. Spinner, spinner. All right, so trial number 1. Each of you please put the spinner on there and flick it. Okay, so let's see, we have Brittany on A and you got a 2. And B, you got a 5. Okay, so we can see clearly B is the winner there. We can also see that a 2 happened for one and a 5 happened for the other. Okay, spin again.
4. 5.
Okay, so B wins again. Do it again.
9.
3.
Ah, A won. Okay, so what I want you to do is I want you to repeat this process 30, so we'll have 30 rows here. Okay. Each time we can tell on a given row who won, A or B. If you want, you can write that next to it, but you don't have to. You can look at it later. And you can use that information to then fill out this chart right here, because you'll be able to look and see for spinner A, how many times did 2 happen? How many times did 4 happen? How many times did 9 happen? What we should expect to have happen, because the spinner is, we think the spinner's fair, right? It shouldn't be biased, unless you're a really good flicker. But I should expect to get about 10 2s, about 10 4s, about 10 9s. Does that make sense? Because I'm doing 30 times. Each is equally likely to happen, I think. But the other thing we want to answer is, like Christian was saying, does it seem fair? Okay, so let's get a few minutes. So everybody play that a little bit and see what happens. I have a spreadsheet version of this. So let's see, do we have even, oh no, we don't. We have an extra version. Let's see, I have some spinners, but I'm kind of running out. Let's see, Kelly and I can play. Greg, Christian, you can play. Let's see, I got a couple paper clips here, Kelly. You have a spin, okay. You get an online spinner, yeah, I thought about that too. Christian, you can use either regular, which has an online spinner, or not.
9.6.
I do this. Yeah. You want to compare spinner A to B, so you spinner, which spinner are you going to be? You spinner A, Christian, you are spinner B, Christian.
I believe I have the better odds.
4.
Oh, okay.
2.
Let's see which one comes here. And, oh, let's see, Debbie out there. Debbie, you got some kind of spinner?
Not yet, no.
Not yet, okay.
9.
There is a way to simulate this on a spreadsheet, but it's quite complicated, so we're not going to go there today. So I'm using a paperclip spinner here. Oh, I should bring up my spreadsheet just to show some more data.
Okay, so the answer was 7.
All right, Kelly, can you start spinning for spinner A and writing down what you get each time? Oh,
7.
let's see.
3. 3. 3. Okay. 3. Let's go. Give me all the A's first.
2, 4, 9, 9, 2, 4, 2, 4, 4, 9, 7, 2, 4, 16, 2, 3, 4, 4, 2, 9, 2, 9, 2, 9, 4, 9, 4, 4, 4, 5, 5, 3, 7, 7, 5, 5,
Yeah.
3, 3, 5,
It's not
7, 3, 7,
Spin in and
5, 5, 5, 3, 3, 3, 7, 7, 7, 7, 7, 5, 5, 7,
Pencil.
7, 7,
Pencil.
7, 7.
Okay.
Okay, what?
7,
I guess we love the second one.
5, 5, 7, 3, 3.
Spinner A.
7,
7.
4, 5,
Why do I only get 29?
3. Yeah, 30. 3. 7. 30.
I have 32, but
Five.
There, catch up to you. Oh, there's some stuff. Okay, let me write mine. I'm going to show you 2.
7.
Sometimes spin.
7.
And let's see, Debbie, I will send you some of my spinner results so you'll have more data.
Okay, that sounds good.
Wait, how do we figure fluency?
Frequency, count. Frequency is count. How many times did 2 come up? How many times did 4 come up? How many times did 9 come up? So,
What's the difference between frequency and tally?
same thing. Tally would be like if you did tally marks.
Oh.
You might not need to do
That's
that.
confusing.
Yeah. Well, I'm just having you do the lab a different way than they intended. This way gives us more information.
Yeah, eight.
There's an interesting thing though about the age slot, because for some reason, if you get the 2 and 9, it's like no matter what you like.
Oh, eight, yeah, you're right. I see what I missed there.
What does it owe to see who won?
I got a 2, you got a 5. It's not enough.
Yeah, B won.
Oh, I'm thinking Brittany.
Okay, so there is the data. So then next week we can write down. All right, let's see, another spreadsheet.
So the frequency would be,
Frequency is how many times did the 2 show up? How many times did the 3 show up?
oh, then what's the tally?
Tally is if we did it by making tally marks. So here, we're writing down the number. The author of this lab intended you to just to make a mark on the paper every time 2 came up. You know, tally marks like 1, 2, 3, 4, 5 across. So we, hash
So they're
marks.
pretty much the same.
So we're just skipping the tally. Okay, it's the same thing.
So, how do you determine the winner?
The winner is combined the, how many wins there were in comparison of each.
Are you guys done?
It's been 3 times. And the total number of wins versus losses. Like,
Oh, yes.
50.
I didn't get 50-50.
15.
you get
I got 14.
8 came up, 2 came up 8 times, 4 came up 13 times, 9 came up 9 times. So Gary, are we doing that like,
16.
are we doing this where it's like each time we compare?
Yeah. So what did you get on the first row? What did he get on the first row? What did you get on the second row? What did he get on the second row?
I mean, the question you're asking?
no, not really. So look, I have this figure here. Where's this data go on here?
So what I was hoping you would do is record it differently. So the table I drew on the board earlier,
Oh, yeah.
I was hoping
Studio winner.
on your first row, you wrote down what you
Yeah,
got,
we
and
got
he wrote what
14
he
for
got.
A and 16 for B.
I'm doing that.
And 16 for B.
I'm doing that.
And then we got, 9 for A.
If you can catch up to
21
it,
for
right?
Okay, so
You're having too much fun with that computer spin.
it's awesome.
Kelly, do
It
you
is
know how
cool, I
many
know, those are
each
great.
A
They're,
and
yeah,
B won?
those are fun.
What?
Do you know how many each A and B won?
On yours,
No, I know, do you have?
did you count it up? Yeah, so how many times, yeah, count
You
how
said
many
you
E's
had
there are.
what?
A had 14 and B had 16.
Wait, no,
That's for them.
that's ours.
Oh, that's it.
Oh, I was
A
like,
had
Oh
9
my
and
gosh,
B
I'm
had
so
21.
like 9 and 21.
I'm like, whoa, that sounds really familiar.
Can you guys think of that?
It won 17 times, we won 13 times.
14, 13.
Okay, so let's get some class data collected already up here. So wins, A versus B. So Kelly, what did you have again? How many times did your A win?
17.
17, and your B won? 13. Okay, you guys,
16 for B,
16
Sorry.
for B and
14 for A.
oh, obviously, right. Okay. And what'd you guys get?
9 for A and 21 for B.
Christian and Jones over there doing something different, so let's see, what do I have? I, in one of mine, what's wrong one? The other one, this one. I counted, let's see, why don't we do 20 times so I can follow the rules right? Okay,
So you have the 8 over B.
so let's see, I can scale that up. 35%, 30, so it's about 10 for A roughly, and almost 20 for B. Pretty close. So on one of mine, I got 10 for A and about 20 for B. So let's add those up to get a group amount. So for the group, it looks like we have 50 A's. So I think I'm adding those up to, and then 70 B's. So that adds up to what, 120,
Yeah, that's what we need.
which is 30 times 4. Yeah, okay.
I'll go with B section.
So let's think, so does it look like B is more likely to win based on this data?
Yes.
Yes.
Yeah, it does look like it. So 7 12. Anybody know what that is in a calculator? 7 out of 12.
0.58 repeating.
0.5, let's call it 9-ish, roughly. And so this one, that means B would be what, 0.41? Did I do that right? Ish. 5 out of 12, 50 out of 120. So that's what we're getting for the, now what kind of probability is this? Is this theoretical probability or experimental probability?
Experimental.
This is experimental, yeah. How, is there a way to figure out the theoretical probability of this? What 2 tools have I used to figure out theoretical probability so far?
Full spots on the board.
Well, how many different ways, what, Minerva? No. So, Kelly? Minerva, what was that?
Is it favorable outcomes over total?
Yeah, if I could find all possible outcomes, do we know how many different ways this can happen when you guys spin against each other? How many different ways are there? No. That's how many times we played.
Is it the group?
And so you played, what spinner?
I played B.
You played B. How many different outcomes did you have for spinner B? 3, right?
Yeah.
There were 3 different numbers, and Minerva, you had 3 different numbers, right? So if you had 3 options and Minerva had 3 options, how many are there total? 9, 3 times 3.
Oh, okay.
There's 9 ways it can come out. And to figure that, what those possibilities are, we can either draw a tree or make a table of it. What do you want to do, tree or table? And then we got to stop because we're over time. Tree? Okay, Minerva wants to make a tree. So let's analyze it with a tree. So here's the way I'm going to make the tree happen. You got to pick one person to analyze first. Right? So let's say I'm going to analyze Minerva first. And Minerva was on spinner A. What things could happen when you spin? Want to give 3 numbers in order, Minerva? For A?
You get
Yeah.
2, 4, 6.
So 2, 4, 11.
2, 4, no, I don't even know how many times. I just know what could happen. You could get a 2, a 4, or a 9, is that right?
Yeah.
Yeah. So Minerva spins, and either she ends up with a 2, or she ends up with a 4, or she ends up with a 9. Let's suppose she got a 2, right? And then Adrian spins for B. That's a B. Not. And let's see, what were your possibilities, Adrian? 3, 5, and 7?
Yes.
Is that right? Okay. So she got a 2. You could either spin a 3, or a 5, or a 7. And that could have happened any time. If Minerva got a 4, you could still get a 3, or a 5, or a 7, right?
Yeah.
And if she got a 9, you're still going to get a 3, or you're going to get a 5, or you're going to get a 7. Those are the possible ways things can happen. So the ends of the branch represent the 9 things that could happen. And then we can write down who won each time. So choose a different color. So one possibility is Minerva got a B and Adrian got you got a 2 and Adrian got a 3. Who won? B, right? So I'm just going to write a letter. So B wins here, B wins here, and B wins here. So B won all the time if Minerva got a 2. Moving on to the next one. B loses here, A wins. But then B wins and B wins again. And then 9 is the killer. Every time Minerva gets a 9, Adrian might as well not spin. But she does, but all the time, you know, Minerva wins. So these are all the possible ways this game can happen. The 3 possible things that can happen on Minerva's spinner A, and the 3 possible things on Adrian's spinner B. And out of those 9 things, we see that B happens to win how many times? 5. Yeah. So the probability of B winning is 5 nights, and the probability of A winning is 4 nights. And anybody remember what happens when you divide by 9? Repeating. You get the repeating numerator. So roughly we could say that probability of A winning is like 44.4%-ish, and the probability of B winning is 55.6%-ish if I round, which isn't too far off from our experimental values, 59 and 41. B won a little more often than the theory says it should happen. That's luck. We'll talk more about how theoretical and experimental are related next time. They've always been on black and what? What game? Roulette. Oh, roulette? I'm afraid to play roulette.
Yeah, you could lose too much money too fast.
Stick with the penny slots, guys. Penny slots.
Or just don't.
Oh, do you know the definition of lottery? It's a tax on people who are bad at math. Wow.
Oh. He's saying something to you.
You play the lottery?
All the time.
No, I don't.
It's worth trying, let's see.
I don't like to.
Oh, counting, yeah, so if somebody's good at keeping track of cards, then they can kick butt playing
Oh, blackjack.
blackjack, yes.
I swear this team's getting closer.
Yeah, not many people are good.
There's like 8 decks in a shoe, so.
That's impossible to count, yeah.
You can't count
Even-
cards that way.
Even Rayman can't count that.
No, there are some games though where all you have to do is keep track of how many times this card's been laid down. You just focus on your cards and what's been laid down. You know, stack versus
Oh, Hillary, how's that? Okay.
I'm coming back.
Hey Debbie, how you doing out there?
I'm fine. I just have 2 questions.
Yeah.
So in the activity, when it gets down to the mutually exclusive events, do we take
Yeah.
the 2 probabilities and add them together?
Yeah, so mutually exclusive means they have nothing in common. And so if they have nothing in common, we can add them together without worrying about any overlap.
Okay.
Yeah.
And then you probably went over this at the beginning of class, but did you happen to grade the tests?
I graded the in-class part, and I'm a third through the take-home. So I need to email, I didn't get to email yours out yet, but I'll do that today.
Okay.
So you'll get an email with the in-class part, and then I'll post my key in the doc sharing.
Okay.
Is that it?
Yep.
Okay, yeah, so then hopefully by tomorrow, I'll email you the second part. And we're gonna do, oh yeah, here's some other stuff you missed. So you correct the in-class, don't worry about correcting the take-home. And
Okay,
then,
correct in class.
yeah. And for the final exam, we're gonna do that in 2 parts. I want people to retake the test they did the worst on. And that could happen at the end of the last week of classes or the beginning of finals week. And then we'll have a regular final on Wednesday.
Okay, so on finals week, there's going to be class both Monday and Wednesday.
So we were talking about having a partial review day on Monday. So the first part of class will review some things from the last 2 tests. And the second part, people will redo whatever test they want to redo.
Okay. Okay.
And then there's a practice exam already a practice final already in the doc sharing. And I'll probably post another one.
Okay.
Okay. All right, so you'll get a couple emails from me soon. Let me know if you have any questions after you get them.
All right, I will. Thank you.
Okay, welcome. Bye-bye, Debbie.
Bye.